Welcome back. So we've now seen how to monitor the progress and performance of our model on a held-out validation set using two different keyword arguments in the model.fit method. Now we'll see how you can include regularization techniques into the model training that have the effect of constraining the model capacity and preventing overfitting. In particular, we're going to look at using L2 weight regularization, which is also known as weight decay in the context of neural networks, as well as L1 weight regularization. And you'll see how to include dropout in your models. Let's start with adding in weight decay to our model. Here we have a feed-forward network with a single hidden layer. This is a binary classification model. As you can see, the output has just one neuron and a sigmoid activation function. We can add in weight decay when we define our model. Dense layers, as well as convolutional layers, have an optional kernel regularizer keyword argument. To add in weight decay, or L2 regularization, we set the kernel regularizer argument equal to a tf.keras.regularizers.l2 object. This object is created with one required argument, which is the coefficient that multiplies the sum of squared weights in this layer. Remember that a dense layer has weights and biases, and the weight matrix is sometimes called the kernel. Here we've set the weight decay coefficient to be equal to 0.001. Once we've built the model together with the weight decay, we can compile and fit the model as normal. The weight decay penalty term is automatically added to the loss function when we compile the model. So here our loss function would be the binary cross entropy, calculated using the model predictions and the true labels, plus the sum of squared weights of the first layer of our model, multiplied by the weight decay coefficient of 0.001. This sum of squared weights term has the effect of penalizing large values of the weights, which encourages the model to find a simpler function that fits the data. This means the model is less likely to overfit to the training set. Instead of L2 regularization, we could use L1 regularization. In this case, the penalty term is a sum of absolute weight values instead of a sum of squared weight values. We can use L1 regularization in a very similar way. This time we're creating a tf.keras.regularizers.l1 object and passing that to the kernel regularizer argument. The regularization coefficient this time is 0.005. L1 regularization has the effect of sparsifying the network weights, or in other words, it results in some of those weights being set to 0. And in fact, there's no reason why you couldn't use both L1 and L2 regularization. Here we've created a tf.keras.regularizers.l1l2 object and passed that to the kernel regularizer argument. The coefficients for the regularizers can be set independently, so now the regularizer object has got two keyword arguments, one for the L1 regularization and one for the L2 regularization. In all of these examples so far, we've only been applying regularization to the weight matrix of the first dense layer. It's quite typical to only apply regularization to the weight matrix or the kernel of a dense or convolutional layer. However, it is perfectly possible to include regularization for the bias as well. Here we can see how to do just that. In the constructor of a dense or convolutional layer, there is also an optional bias regularizer argument. We can pass this argument, a regularizer object, in just the same way as we did before. And again, this will add a penalty term to the loss function, this time for the bias parameters. The final thing I'd like to show you is how to include dropout in your network. Dropout also has a regularizing effect in neural networks, and in TensorFlow we can include dropout as just another layer. So here you can see we're importing not only the dense layer as before, but also the dropout layer. Now in our sequential model, we've included the dropout layer in our list of layers. The dropout layer has a required argument, which is the dropout rate. Here the rate has been set to 0.5, and that means that each weight connection between these two dense layers is set to 0 with probability 0.5. This is sometimes referred to as Bernoulli dropout. since the weights are effectively being multiplied by a Bernoulli random variable. Each of the weights are randomly dropped out independently from one another, and dropout is also applied independently across each element in the batch at training time. Again, we can compile and fit our model as normal, with dropout layers included in our model. But remember that when we're using dropout, we typically have two different modes for how we run the network. At training time, we randomly drop out weights in the way that I've described, and we can think of this as training mode. However, when we're evaluating our model, or making predictions from it, we stop randomly dropping out the weights, and we can think of this as testing mode. These two modes are automatically handled behind the scenes by the model.fit, model.evaluate and model.predict methods, but it's worth bearing in mind that this is happening in the dropout layer, and later on we'll look at ways of getting more lower level control over the network, and you'll see then how these two modes of operation for dropout can be controlled. We're now starting to increase the sophistication of our models by including important concepts such as validation and regularisation into our training workflow. You can also now include dropout as an additional layer, and later on in the week you'll see how to include batch normalization, also as an additional layer type. In the following coding tutorial, you'll implement regularisation into your model and see for yourself firsthand how these techniques help your model to generalize beyond the training data.